In a hospital basement somewhere tonight, a person is lying inside a ring of detectors while a machine assembles a picture of the inside of their body. That machine works because of antimatter. A tracer in their bloodstream is throwing off antiparticles, and each one travels a millimeter or two, finds an ordinary electron, and both of them stop existing. The flash of that ending is the only thing the machine can see. It cannot photograph the antimatter. Nobody can. We have never once detected this substance by observing it, only by catching the instant it is destroyed. Astronomers use the same trick on the Milky Way, and for 55 years they have been building a map of our galaxy's antimatter that nobody has been able to explain. Recently, someone took 20 years of that data and subtracted the galaxy out of it to see what was underneath. The sky did not go dark, so what is out there, in the empty part of the sky, glowing at the one colour that only ever means something has been annihilated? Make yourself comfortable, subscribe if you have not, and stay with us, because by the end of tonight you will know exactly what is leaking out of our galaxy, and why the unsettling part turns out not to be the antimatter at all. Let's begin. Part 1. Only the death makes light. There is a particular colour of light that only exists when something has been destroyed. You cannot see it. It sits far outside the range your eyes evolved to handle, up past visible light, past ultraviolet, past X-rays, in the part of the spectrum we call gamma rays. But it is a colour in exactly the way red is a colour. It has a specific energy, a specific frequency, a specific and unmistakable identity. And every single photon that carries that identity was made in the same way, by the same event, everywhere in the universe, without exception. It is made when a particle of matter meets a particle of antimatter, and both of them stop existing. The energy is 511,000 electron volts. Astronomers write it as 511 kilo electron volts, and say it out loud as 511, the way you might say a street address. And it is a street address, in a sense. If you build a telescope that can see gamma rays and you tune it to that one narrow band, you are not looking at stars. You're not looking at gas or dust or galaxies. You're looking at a map of annihilation events. Every bright patch on that map is a place where antimatter is being destroyed right now, in enormous quantities, and has been for as long as anyone has looked. I want to sit with that for a moment before we go anywhere, because it is the thing that makes everything else in this video strange. We have no way of seeing antimatter, not in space, not at any distance. There is no telescope that can point at a cloud of positrons and photograph it, the way we photograph a nebula. Antimatter in bulk, at astronomical distances, is completely invisible right up until the instant it ceases to be antimatter, and then, for a fraction of a second, it is the brightest thing in that part of the sky. Only the death makes light. So let me tell you what a positron actually is, because everything after this depends on it, and it is simpler than people expect. Take an electron. It is the particle that orbits atoms, carries electricity through wires, and does essentially all of the work of chemistry. It has a certain mass, which is very small, and a negative electric charge, and a property called spin. Now imagine a particle that is identical to the electron in every measurable way, the same mass exactly, to as many decimal places as anyone has ever managed to check, the same spin, except that its electric charge is positive instead of negative. That particle is the positron. It is the electron's antiparticle. It is not a different kind of thing. It is the same thing, reflected. It is worth seeing the moment we found out, because it is a photograph, and it is a strange thing that the mirror side of the universe was first proven by a photograph. Imagine you're looking at it. It was taken in 1932 at Caltech by a 27-year-old physicist named Carl Anderson, using a device called a cloud chamber, a sealed box full of supersaturated vapor, sitting in a strong magnetic field, with a lead plate running across the middle. When a charged particle rips through vapor like that, it leaves a thin trail of droplets behind it, the way a jet leaves a contrail, and in a magnetic field that trail curves. Positive charges curve one way, negative charges curve the other. The tighter the curve, the lower the momentum. In the photograph there is a single thread of droplets coming up from below, passing through the lead plate, and bending. It is bending the wrong way. It cannot be an electron because an electron would curve in the opposite direction. It cannot be a proton because a proton with that much momentum would have punched through the lead plate almost undisturbed instead of losing energy, the way this track did, and a proton with that little momentum would have stopped dead. The only object that fits the curve is a particle with the mass of an electron and a positive charge, which nobody had ever seen, and which one man had predicted 4 years earlier from an equation whose negative energy solutions he had found so troubling that he spent years trying to interpret them away. That is the whole discovery. A curved line of water droplets, bending the wrong way. From that photograph comes everything else in this video. Almost everything you have ever encountered is made of ordinary matter. The chair you're sitting in, the air moving in and out of your lungs, the phone or the speaker this is coming out of, the sun, the planets, the stars you can see on a clear night. All of it is protons and neutrons and electrons, arranged in various ways. But the equations that describe those particles do not prefer them. For every kind of matter particle, there can be a corresponding antiparticle, with the charge flipped. Antiprotons exist, antineutrons exist. Antihydrogen has been made in a laboratory, atom by atom, and studied. The universe permits a complete mirror version of everything we are made of. And here is the part that makes antimatter different from every other exotic thing in physics. When a particle meets its own antiparticle, they do not bounce, they do not scatter, they do not fuse into something heavier. They vanish, completely, and every bit of the mass they used to have comes out as energy. This is worth pausing on because it is genuinely unique. Every other energy-producing process we know is a fraction. When you burn a log, you release something like 100 millionth of the energy locked in that log's mass. When you split uranium in a reactor, you get about 1/10 of 1%. When the sun fuses hydrogen into helium in its core, the most efficient sustained energy process in the solar system, it converts about 7/10 of 1% of the mass into light. Annihilation converts 100%. All of it. There is no residue, no ash, no leftover nucleus. 2 particles go in and pure energy comes out, and nothing in nature is more efficient than that, because nothing in nature can be. For an electron and a positron, the total energy released is 1.022 mega-electron volts, the summed rest mass of both particles, converted with perfect efficiency. And when they annihilate at rest, that energy comes out as 2 photons, flying away from each other in exactly opposite directions, each one carrying precisely half. 511 kilo-electron volts, each. That is where the number comes from. It is not a coincidence. It is not a resonance. It is not an accident of some particular environment. It is just half the mass of an electron expressed as light, which means the number is the same in the Andromeda Galaxy as it is in a hospital basement, the same today as it was 10 billion years ago. It is a universal constant wearing the costume of a colour. This has a practical consequence that has shaped an entire branch of astronomy. Because the 511 kilo-electron volt line can only be produced one way, its presence is proof. There is no astrophysical process that mimics it. No hot gas glows at exactly that energy. No nuclear transition sits exactly there by chance. If you detect a narrow spike of gamma rays at 511 kilo-electron volts coming from some direction in the sky, you have not found evidence of antimatter. You have found antimatter, or rather, you have found the specific moment of its disappearance, which is the only form in which it will ever consent to be found. We use the same trick on Earth, incidentally, and most people have benefited from it without knowing. A PET scan, positron emission tomography, works by injecting a patient with a mildly radioactive tracer that decays by emitting positrons. Each positron travels a millimeter or two through tissue, finds an electron, and annihilates. 2 photons of 511 kilo-electron volts fly out in opposite directions. A ring of detectors around the patient catches both ends of that line, and a computer works backwards to find where the annihilation happened. Millions of those events, assembled, produce a 3-dimensional image of the inside of a living person. The entire technology is built on the same fact this video is built on. We cannot see the antimatter, we can only see the exact place and moment it stopped. So now hold 2 things at once. The first is that antimatter is the most energetic substance physics allows, and it exists, and it is real, and we can make it and measure it, and even take pictures of the inside of a human brain with it. The second is that when astronomers turn that same detection method on the Milky Way, they find that our galaxy is destroying antimatter at a rate that no one has ever been able to explain. Not roughly explain, not explain with a factor of 2 disagreement. Explain at all. Every candidate source that has been proposed over the last half-century either makes the wrong amount, or makes it in the wrong place, or makes it at the wrong energy, and after 55 years of trying, the question of where the Milky Way's antimatter comes from is still open. And that was the situation, uncomfortable but stable, until somebody looked at 20 years of accumulated data, subtracted the galaxy from it, and discovered that the sky did not go dark. Part 2. The reason. Anything is here at all. Before we go looking for the Milky Way's antimatter, we have to deal with a much older problem, which is that there should not be any matter either. This is not a rhetorical flourish. It is the plain reading of the physics, and it has been an open wound in cosmology for the better part of 70 years. The equations that govern particle production are, as far as anyone has ever been able to test them, almost perfectly even-handed. When you make particles out of pure energy, and that is exactly what the early universe was doing, at temperatures that make the core of the sun look like a cold morning, you make them in pairs, one particle, one antiparticle. A positron does not come into existence alone. It comes into existence alongside an electron, and the two of them are born out of energy together, in a ledger that balances exactly. So run that forward. The universe begins, extremely hot and extremely dense, and it is making pairs at an incomprehensible rate. Then it expands, and as it expands it cools, and below a certain temperature it can no longer create new pairs. What it can still do is destroy them. Every particle finds an antiparticle. Every pair annihilates. Every annihilation converts the pair back into light. And when the accounting is finished, the universe should contain photons. Only photons. A perfectly uniform sea of radiation, cooling forever, with nothing in it. No stars, because there is no hydrogen to make them out of. No planets. No chemistry. No structure of any kind, anywhere, for all of time. That is what the symmetric version of the Big Bang produces, and it is a universe in which this video does not exist and neither do you. Obviously that is not what happened. So somewhere in the first fraction of a second something tipped. The size of the tip is known reasonably well, and it is one of my favourite numbers in all of science because it is so small and so consequential at the same time. For roughly every billion antiparticles that existed in the early universe, there were about 1,000,000,001 particles. That is the whole margin. 1 part in 1,000,000,000. Everything that could pair off did pair off. Those annihilations produced a flood of photons that is still with us today, stretched by the expansion of space into the faint microwave hiss that fills every direction of the sky. And when the annihilation was over, and the light had been released, what was left standing was the leftover, the one particle in every billion that arrived at the end of the process and found that there was nobody to annihilate with. That leftover is everything. Every atom in your body is a survivor of that accounting. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it was assembled from particles that made it through the great annihilation because there happened to be a slight surplus of them. The sun is made of leftovers. The earth is made of leftovers. Every star you can see on a clear night, and every star in every galaxy and every photograph ever taken, is made from the 1 in a billion residue of a reaction that was supposed to cancel out completely. We are not the main event. We are what was left over after the main event finished. And the light from that main event is still arriving, from every direction at once, all the time, at a temperature just under 3 degrees above absolute zero. That is the part that gets me. The cosmic microwave background is not just an artifact of the early universe. It is, in a real and literal sense, the light of the annihilation that nearly erased us. It is the receipt. Now, why did the tip happen? Physics has a name for the general phenomenon, which is a good sign that we understand part of it, and a much less impressive record when it comes to the actual quantity, which is a good sign that we do not understand most of it. The name is CP violation. C stands for charge conjugation, the operation of swapping every particle for its antiparticle. P stands for parity, the operation of reflecting everything in a mirror. For a long time it was assumed that if you did both of those things to any physical process, you would get another perfectly valid physical process, running identically. Matter and antimatter would be exact mirror images, behaving in exactly corresponding ways. They are not. In 1964, an experiment at Brookhaven found that a certain kind of particle called a neutral kaon decays in a way that very slightly violates that symmetry. The effect is tiny, a fraction of a percent, but it is real. It has been confirmed many times over, and it earned a Nobel Prize. Since then, CP violation has been found in other particles as well. Matter and antimatter are genuinely not perfect mirrors of each other. There is a thumb on the scale. The problem is the size of the thumb. When you take the CP violation that has actually been measured in the laboratory and feed it into a calculation of how much matter should have survived the early universe, you get an answer that is far too small. Not by a factor of 2, by many orders of magnitude. The known asymmetry cannot account for the surplus that we can see with our own eyes every time we look at anything at all. So the honest position in 2026 is this: we know the universe cheated. We can even name the general category of cheating. We cannot explain how it cheated by enough to leave a universe behind. That is the backdrop. It is the reason antimatter is not merely an interesting substance but a genuine open question about why anything exists. And it is the reason astronomers care so much about a faint gamma-ray line coming from the middle of our own galaxy. Because if there is antimatter out there in quantity, if there are places in the universe where the mirror side of the ledger is still being written, then the story of how the balance broke might not be finished. There is a framework for what a successful explanation would have to look like, and it comes from an unexpected place. In 1967, the Soviet physicist Andrei Sakharov, the same man who would later become one of the most prominent dissidents in the Soviet Union and win the Nobel Peace Prize for it, wrote down 3 conditions that any theory of the matter surplus must satisfy. The universe must be able to violate the conservation of baryon number, which is to say it must be possible to make a proton without making an antiproton. The universe must violate both charge symmetry and the combined charge parity symmetry, so that the two sides of the ledger genuinely behave differently. And the universe must pass through a period where it is out of thermal equilibrium, so that whatever imbalance gets created does not simply get undone again as things settle. All 3 of those conditions are, in principle, satisfiable within known physics. The trouble is entirely quantitative. The standard model of particle physics contains charge parity violation, but not nearly enough of it. It contains a mechanism that could in principle violate baryon number, but only under conditions that seem not to have occurred. And the electroweak transition in the early universe, which was once hoped to provide the out-of-equilibrium moment, appears to have been too smooth. Every ingredient is on the shelf, and the recipe still does not work. The scale of the shortfall is easy to state, and hard to absorb. If you take the amount of charge parity violation that has actually been observed in kaon and B-meson decays, and run it through the calculation, you predict a surviving matter density something like 10 billion times smaller than the one we live in. Which means that either there is a source of asymmetry we have not found, in some sector of physics we have not probed, or the asymmetry was not generated by particle physics at all, but was somehow built into the initial conditions of the universe, a possibility most physicists find deeply unsatisfying, because it amounts to saying it was like that when we got here. There is another number that makes the same point from a different direction. Count the photons in the cosmic microwave background and count the protons in the universe, and the ratio comes out at roughly 1.5 billion photons for every proton. That ratio is a fossil. It is the direct record of the annihilation, 1.5 billion units of light for every unit of matter that survived. When you look at that number, you're reading, in a single figure, the size of the massacre and the size of what escaped it. And this is the moment to say the thing plainly, because the rest of the video sits on top of it. You are made of the survivors, not metaphorically. The particular protons and neutrons in your hands right now trace their existence back to the fact that, in the first fraction of a second of the universe, there was a slight surplus of them and no corresponding antiparticle waiting. Everything that had a partner is gone. It left as light, and that light is still passing through you, right now, from every direction, at a temperature of 2.7 degrees above absolute zero. Existence, in this universe, is not the default outcome. Existence is what happens to the ones that had no partner. Which brings us to a very specific afternoon in 1970, and a balloon, and a group of people who were looking for something else entirely. Part 3. A balloon over Texas. The discovery that there is antimatter dying in the middle of our galaxy was not made by anyone who was looking for antimatter dying in the middle of our galaxy. In 1970, a group from Rice University in Houston, led by a physicist named Robert Hames, was flying gamma-ray detectors on high-altitude balloons, This was how gamma-ray astronomy was done at the time, and to a surprising extent it is still how some of it gets done. The atmosphere is opaque to gamma rays, which is excellent news for life on the surface and extremely inconvenient for astronomers. So if you want to catch them, you have to get above almost all of it. A balloon can carry an instrument to around 40 kilometers, roughly 4 times the cruising altitude of an airliner, where the air above you is thin enough to see through. You get a few hours, sometimes a day, and then you come down. The Rice detector was pointed at the center of the galaxy, which in the northern summer sky sits low in the direction of Sagittarius, and it was looking for a general glow, the broad, featureless gamma-ray emission that hot processes produce. What it found instead was a bump, an excess of photons piled up near 500 kilo electron volts, sitting on top of the smooth background like a hill on a plain. Nobody knew quite what to make of it. The instrument was a scintillator, which is to say a crystal that flashes when a gamma-ray hits it, and scintillators are not precise. They can tell you roughly how much energy arrived, but the uncertainty is broad enough that the measured position of that bump wandered depending on who analysed the data and how. The early numbers came in low, somewhere around 476 kilo electron volts, and that was low enough to start people speculating about exotic possibilities. Perhaps it was 511 kilo electron volt annihilation light that had been redshifted on its way out of an extremely strong gravitational field, which would mean the source was something enormously compact, sitting right at the galactic centre. Perhaps it was some nuclear line nobody had thought of. For most of a decade the field argued about a bump. The argument ended in 1978, and it ended because of a material. A team led by Marvin Leventhal flew a detector built around cooled germanium instead of a scintillating crystal, and germanium changed everything. In a germanium detector, an incoming gamma-ray liberates charge directly inside a semiconductor crystal that has been cooled to around the temperature of liquid nitrogen, and the amount of charge is very precisely proportional to the energy deposited. The resolution is not a little better than a scintillator. It is dramatically better. The difference between hearing that someone said something and hearing exactly which words they used. When that instrument looked at the galactic centre, the bump resolved into a line, a narrow, sharp spike sitting at 511 kilo electron volts, where the annihilation of a positron and an electron at rest puts it, and where nothing else puts it. There is a moment in the history of a field when a fuzzy anomaly becomes a hard fact, and this was it. Astronomy did not merely have a bump anymore. It had a measurement of antimatter annihilating in the Milky Way, in enormous quantity, continuously, at the present time, not in the early universe, not in a theoretical calculation, now, in the sky above us, in a direction anyone can point to on a summer night. And the narrowness of the line carried a second piece of information that took much longer for anyone to fully appreciate. A line is narrow when the particles producing it are moving slowly. If the positrons had been annihilating at high speed, the light would have been smeared out by the Doppler shift, some photons boosted, some dragged down, the spike blurred into a hump. It was not blurred, it was sharp, which meant the antimatter dying at the centre of the galaxy was not dying in some violent high-energy environment. It was dying cold, drifting through ordinary interstellar gas at temperatures more like a warm nebula than a black hole's accretion disk. Nobody at the time knew how important that detail would turn out to be. Hold on to it. Everything that goes wrong later in this story goes wrong because of it. It is worth understanding just how much work that measurement was. A balloon campaign is not a flick of a switch. The payload has to be built, tested, calibrated against known laboratory sources, and then trucked to a launch site. Palestine, Texas, for most of these flights, or later Alice Springs in Australia, and Fort Sumner in New Mexico. It has to be launched in a narrow weather window at dawn, when the surface winds are calm enough not to tear a balloon the size of a stadium. It floats for hours, drifting with the stratospheric winds while the instrument tracks a point in the sky. Then the payload is cut loose, it parachutes into a field somewhere, and somebody drives out to find it. Every one of the results in this part of the story cost a team of people a year of their lives and produced a few hours of data. Germanium made those few hours worth far more. A cooled germanium detector can distinguish two gamma-ray lines, separated by a couple of kilo-electron volts out of 500, a resolution of a fraction of a percent, in a part of the spectrum where scintillators were working at 10%. That is why the same material is still, half a century later, at the heart of every serious instrument built for this problem, including the one currently being assembled for launch in 2027. Nothing better has been invented. The technology of this entire subject is essentially a story about very pure, very cold germanium. The satellite era confirmed it quickly. HER 03, launched in 1979, carried germanium detectors into orbit and saw the line cleanly. The total flux from the galactic center region settled at roughly 1,000th of a photon per square centimeter per second, which sounds like nothing until you remember that it is being collected from 26,000 light-years away through the entire thickness of the galaxy, and that every one of those photons represents an electron and a positron that have ceased to exist. Run that flux backwards through the geometry, and you get an annihilation rate that is very large indeed, and we will put an exact number on it shortly. The 1980s then did what fields sometimes do, which is convince themselves of something that was not true. Different balloon flights, flown by different groups with different instruments, reported different flux levels for the line. The natural interpretation was that the source was variable, brightening and fading on timescales of months, and a source that varies on a timescale of months has to be physically small, because nothing can change its output faster than light can cross it. Months meant something no bigger than a light month across. That pointed at one object, the black hole at the center of the galaxy. For a while, the textbooks essentially had it. The 511 kilo-electron-volt line was the signature of antimatter production by the galactic center black hole, flickering as it fed. It was not. The Solar Maximum mission, a satellite that had a wide field of view and simply stared for years on end, showed that the emission was steady. It did not flicker. What had varied was not the source but the observers. Instruments with different fields of view, pointed slightly differently, were collecting different fractions of an extended glow and reporting the differences as changes in brightness. The variability was an artifact of the aperture. I want to flag that, because it is going to matter enormously at the end of this video. This specific corner of astronomy has a long and honourable history of confident results that dissolved on closer inspection. It is a hard measurement. The signal is faint, the instruments are complicated, the background is ferocious, and the sky is large. Every single time somebody has announced a structure in the 511 kilo-electron-volt sky, the first responsible question has been whether the structure is in the sky or in the telescope. Keep that question in your pocket. We are going to need it. Because once the variability was gone, and the line was established and the physics was settled, astronomers were left with a signal that was completely stable, completely unambiguous, and completely impossible to explain. And the reason it was impossible had nothing to do with how much antimatter there was. It had to do with where it was. Part 4. The shape that is wrong. Here is the thing that has kept this problem alive for half a century. It is not that the signal is faint. It is not that the measurement is disputed. It is that the light is in the wrong shape. To see why that is a problem, you have to know what the Milky Way looks like from the inside, structurally rather than romantically. Our galaxy has a disk, a flattened wheel of gas, dust and stars about 100,000 light-years across, and only a couple of thousand light-years thick, with the spiral arms wound through it. That disk is where things happen. It is where gas collapses into new stars, where massive stars live their short, violent lives, where supernovae go off, where the interstellar medium is dense enough to be interesting. Our own sun sits in that disk, roughly 26,000 light-years from the center, in a quiet stretch between two arms. And then there is the bulge. At the center of the disk, the galaxy thickens into a rounded swelling of stars, several thousand light-years across, packed far more densely than anything out where we live. The bulge is old. The stars in it are mostly ancient. The gas has largely been used up, and star formation there finished long ago. If the disk is where the galaxy is currently working, the bulge is where it has already finished working and left the result standing. Now, when the Compton Gamma Ray Observatory went up in 1991 carrying an instrument called OSSE, it was able for the first time to do more than measure a flux from a general direction. It could build something resembling a map, and the map it built said something that has never stopped being awkward. The 511 kilo-electron-volt light is concentrated in the bulge, not slightly, overwhelmingly. The old, quiet, star formation finished center of the galaxy is where most of the antimatter annihilation is happening, and the young, active, supernova-rich disk, the part of the galaxy that contains almost all of the machinery anyone has ever proposed for making positrons, is comparatively dim. Later measurements sharpened it rather than softening it. When Integral's spectrometer took over the problem after 2002, it measured the flux ratio between bulge and disk at somewhere around 0.58, with an uncertainty of about 0.13. In terms of actual production rates, that works out to roughly 2 times 10 to the 43 positrons per second, annihilating in the bulge, and about 3 times 10 to the 43 per second in the thick disk, for a total of around 5 times 10 to the 43 per second across the galaxy. Let me put that number in a shape a person can hold. 5 times 10 to the 43 is a 5 followed by 43 zeros, every second. If you tried to count them at 1 per second, it would take you longer than the age of the universe by a factor of about 10 to the 26. In terms of mass, the galaxy is annihilating something on the order of half a kilogram of positrons every second, which does not sound like much until you remember that annihilation converts mass to energy with perfect efficiency, and that half a kilogram of antimatter meeting half a kilogram of matter releases roughly as much energy as the entire nuclear arsenal of the world. And it has been doing that steadily, without interruption, for at least as long as we have been able to check, and almost certainly for a very long time before that. Now, the disk has more of the total than the bulge in absolute terms, 3 units against 2, but the disk is enormously bigger. Per unit volume, per unit of stellar mass, the bulge is annihilating antimatter at a rate that dwarfs the disk, and the bulge is exactly the part of the galaxy with the least star formation, the fewest young massive stars, the lowest supernova rate, and the smallest supply of everything that makes positrons. The proportions do not match anything. The bulge holds somewhere between 10 and 20% of the Milky Way's stellar mass, and it produces well over a third of the signal. Massive stars, which manufacture nearly all of the short-lived radioactive material that decays by throwing off positrons, live and die in the disk. They are not in the bulge. They cannot be in the bulge. The gas required to make them ran out billions of years ago. So the spatial mismatch is not a small discrepancy that better data might resolve. It runs in exactly the wrong direction, and it has run in exactly the wrong direction through every generation of instruments that has looked. There is a comparison available that makes the wrongness of the shape almost tactile, and I think it is the single most convincing way to feel this problem. The galaxy contains a radioactive isotope of aluminium called aluminium-26. It is made in massive stars, and in the supernovae that end them, it has a half-life of about 717,000 years, and when it decays it emits a positron and leaves behind a magnesium nucleus in an excited state, which promptly relaxes by emitting a gamma ray at 1,808 kilo-electron volts. That gamma ray is another one of those unmistakable fingerprints, and because the isotope's half-life is long compared to the lifetime of an individual star but short compared to the age of the galaxy, mapping that line gives you a picture of where massive stars have been dying over the last million years or so. That map exists. It was built by Comptel in the 1990s and refined by Integral afterwards, and it looks exactly the way you would expect. It is a thin, bright band lying along the galactic plane, clumped toward the spiral arms and the great star-forming complexes, with essentially nothing above or below. It is a picture of the disk. It is a picture of where the galaxy makes and destroys its big stars. Now put the two maps side by side. The aluminium map is a stripe along the plane. The annihilation map is a ball in the middle. Those are the same photons in the sense that every aluminium-26 decay produces a positron that must eventually annihilate somewhere and contribute to the 511 kilo-electron-volt sky. And yet the two pictures do not resemble each other at all. There is one more measurement worth having before we go to the suspect list, because it will become load-bearing later. The line is not just narrow. Its exact shape has been measured with some precision. The centroid sits at 511.05 kilo-electron volts, plus or minus 0.03. The width is 2.43 kilo-electron volts, plus or minus 0.14. That width is a thermometer. A line is broadened by the motion of the particles making it, and 2.5 kilo-electron volts of broadening corresponds to gas at a temperature of order 10,000 degrees, partly ionized, which is to say, thoroughly ordinary warm interstellar medium, not a black hole's accretion flow, not a shock front, not anything violent. The antimatter in the middle of our galaxy is annihilating in the same kind of gas that fills the space between ordinary stars at the same kind of temperature. Whatever is making these positrons, they are not dying anywhere near the place where the energy came from. By the time we see them, they have cooled down and settled into the general medium like sediment. The field has, along the way, produced two confident structural claims about this map that both eventually dissolved, and I mention them because they belong to the same family as the claim at the centre of this video. The first was in 1997. An analysis of OSSE data appeared to show the emission extending upward out of the galactic plane, above the centre, in a plume. It was reported widely as an annihilation fountain, a jet of antimatter blowing out of the middle of the galaxy. It was a wonderful image and it made the covers of magazines. Better data did not support it. The extension was not there. The second was in 2008. A study using integral data reported that the disk emission was lopsided, brighter on one side of the galactic centre than the other, and proposed that this asymmetry matched the distribution of a particular class of object called low-mass X-ray binaries, which would make them the source. It was published in Nature. It was for several years the leading candidate explanation. As more data accumulated, the asymmetry weakened, and the interpretation is no longer standard. Neither of those was fraud, or sloppiness, or anything to be embarrassed about. They were honest readings of the data available at the time, in a field where the data is genuinely marginal and the sky is genuinely large. But they establish a pattern, and the pattern is that structures in this particular map have a habit of not surviving. What has survived, across every instrument and every decade, is the core morphology. The bulge is too bright. The disk is too faint. The line is narrow, which means the positrons are cold. And the total rate is enormous. Those four facts together define the problem, and they have defined it since before most people watching this were born. Astronomers have a name for it. They call it the positron puzzle, and the puzzle is not really about how much antimatter the galaxy has. It is about which suspects could possibly have put it there, and every single one of them has an alibi. Part 5. Every suspect has an alibi. So let us go through the suspects properly, because the way this problem fails is more interesting than the fact that it fails. Start with the most solid ground there is, which is radioactive decay. There are isotopes in the galaxy that produce positrons as a matter of routine nuclear physics, and unlike almost everything else on this list, we do not have to guess at their abundance. We can measure it directly, because the same decays that produce positrons also produce characteristic gamma-ray lines that we can map. Aluminium-26 is the headline case, and I have already described its 1808 kilo-electron-volt line. When you take the total brightness of that line across the whole sky and work backwards, you find that the Milky Way contains, at any given moment, roughly 2 solar masses of aluminium-26, 2 entire suns' worth of a radioactive isotope distributed through the disk, decaying continuously, every decay releasing a positron. That is a real inventory, measured rather than assumed, and it is a substantial contributor. Titanium-44 is the second case. Its half-life is around 60 years, which is short enough that it only exists where a supernova has gone off recently. It has been detected directly in the Cassiopeia A remnant, which is one of the great satisfying results in gamma-ray astronomy. You're looking at material forged in a specific explosion, whose light reached Earth around 350 years ago, still decaying. It produces positrons too. But because the half-life is so short, the standing amount in the galaxy is small. Then there is the big one, which is type Ia supernovae. When a white dwarf detonates, it produces something like half a solar mass of radioactive nickel-56, which decays to cobalt-56, which decays to iron. That chain is what powers the visible light curve of the explosion. The reason a type Ia supernova stays bright for weeks is that it is being heated from inside by radioactivity, and the cobalt-56 step throws off positrons in prodigious numbers. In terms of raw production, type Ia supernovae are by far the largest positron factory in the galaxy. The trouble is escape. Those positrons are born far inside an expanding ball of dense debris, and for the first weeks and months that debris is thick enough that almost all of them annihilate before they ever get out. The fraction that escapes into the interstellar medium is the entire question, and nobody can calculate it reliably, because it depends on the geometry of the magnetic field tangled through the ejector, and there is no way to measure the magnetic field geometry inside a supernova. Published estimates for the escape fraction range from well under 1% to several percent, which is a range wide enough to drive almost any conclusion you like through. But notice that none of this is really the problem. Add aluminium-26 and titanium-44 and a plausible supernova escape fraction together, and you can get within a factor of a few of the required 5 times 10 to the 43 per second. The amount is not the issue. The issue is that every single one of these sources lives in the disk. Massive stars are in the disk. Their supernovae are in the disk. Even type Ia supernovae, which come from older stellar populations and are therefore the best of a bad set, do not concentrate in the bulge anything like strongly enough to explain a bulge-dominated map. Radioactivity gives you the right number in the wrong place, so the field turned to objects that do concentrate in the bulge. Low-mass X-ray binaries are the leading example. These are old systems, a neutron star or black hole pulling material off an ordinary companion star. And because they are old, they trace the old stellar population, which means they trace the bulge. The distribution is right. That is why the 2008 result, the one about the lopsided disk, was so exciting when it appeared. The problem is that nobody has ever measured how many positrons a low-mass X-ray binary actually produces. The number is inferred from models of what happens in the inner accretion flow, and the models have to be pushed hard to deliver enough. It is not impossible. It is unconstrained, which is a different kind of weakness. Pulsars are the next candidate, and they are genuinely prolific antimatter factories. A rotating neutron star with a strong magnetic field generates electric fields so intense that they rip electron-positron pairs directly out of the vacuum, and the resulting pair wind is the reason pulsar wind nebulae glow. There is no doubt at all that pulsars make positrons in quantity. There is a fatal detail. Pulsars make them fast. The pairs are accelerated to giga-electron-volt energies and beyond, thousands of times more energetic than the positrons we are trying to account for. Remember, the line is narrow, which means the annihilating positrons are cold. A giga-electron-volt positron would have to lose essentially all of its energy before it could contribute to the line, and along the way it would produce a great deal of other radiation that we do not see in the right proportion. The same objection applies to cosmic ray interactions with interstellar gas, which certainly produce positrons at high energies for the same reason and with the same problem. Then there is the black hole itself. Sagittarius, a star, is quiet today, remarkably quiet for a supermassive black hole, but there is independent evidence from X-ray reflections off nearby gas clouds that it was significantly more active within the last few hundred years, and possibly far more active than that within the last few million. A past outburst could in principle have injected a large population of positrons into the bulge, in a bulge-shaped distribution, which we would still be watching slowly annihilate. It is an attractive idea. It is also, at present, essentially untestable, because the outburst is over, and the only evidence would be the very signal we're trying to explain. And then there is dark matter, which deserves its own paragraph because it very nearly worked. In 2004, a group led by Celine Boehm proposed that if dark matter particles have masses in the range of a few mega-electron volts, much lighter than the heavy particles most searches were designed for, then their annihilation with each other would produce electron-positron pairs at exactly the sort of energies required. And here is the part that made everyone sit up. Dark matter is distributed in a roughly spherical halo that peaks sharply toward the galactic center. If dark matter annihilation is making the positrons, then the bulge-dominated morphology is not a puzzle at all. It is a prediction. The shape comes out right for free, which is the single hardest thing to achieve in this entire subject. It has been squeezed hard since. The most damaging constraint came in 2006 from John Beacom and Hassan Uexel, and the argument is elegant. If positrons are injected with too much energy, a fraction of them will annihilate while still moving, before they have time to slow down. That in-flight annihilation does not produce a narrow line. It produces a broad continuum at energies above 511 kilo-electron volts. We can measure how much continuum is there. There is very little. Therefore the positrons cannot have been born with much more than a few mega-electron volts of energy, whatever made them. That constraint does not kill the dark matter idea outright. It confines it to a narrow strip of parameter space, and most of the field drifted away from it, not because it was refuted, but because the room it had to live in kept getting smaller. The answer they got is worth the whole detour. The team was led by Jürgen Nodel-Seder, with Sabri and Jean among the collaborators, and their paper appeared in Astronomy and Astrophysics in 2025. What they did was go back to the archive of Comptel, the same instrument that mapped the aluminium line in the 1990s, long since decommissioned along with the rest of the Compton Gamma Ray Observatory. and search it for exactly the in-flight annihilation signal that Beacom and Uexel had used as an upper limit. Not as a limit this time, as a detection. They found it, extended emission at mega-electron-volt energies toward the bulge of the galaxy with the spectral shape that in-flight annihilation produces, and because the shape of that continuum depends on how fast the positrons were moving when they annihilated, it works backwards into a measurement of the energy the positrons had when they were created. The number is about 2 mega-electron volts. 2 mega-electron volts is a very specific and very inconvenient number, and it cuts in both directions at once. It is too high for straightforward beta plus decay from the standard radioactive isotopes, whose positrons emerge with a few hundred kilo-electron volts of kinetic energy at most, an order of magnitude below, and it is far too low for anything relativistic. Pulsars are out by 3 orders of magnitude. Cosmic ray interactions are out. Anything involving a jet is out. Sit with what that means. After 55 years, we finally have a direct measurement of the energy at which the galaxy's positrons are born. And there is nothing in the standard catalogue of astrophysical objects that makes positrons at that energy, and only that energy. The measurement did not narrow the field down to a winner. It narrowed the field down to nobody. So that is the lineup. Radioactive isotopes, right amount, wrong place. Low-mass X-ray binaries, right place, unmeasured amount. Pulsars and cosmic rays, right amount, catastrophically wrong energy. The black hole, plausible, untestable. Dark matter, right shape, tightly constrained, out of fashion. For half a century that has been the state of the case, and the 2025 result made it worse rather than better. We now know more precisely than ever what we are looking for, and the description fits nothing we know about. Which means that before we can understand why the new hotspots are impossible, we have to understand the one property of these positrons that has been quietly deciding the whole argument from the beginning. They are slow, and they have to be. Part 6. Why it has to be slow. An electron and a positron do not necessarily annihilate the moment they find each other. Most of the time, in the conditions that actually exist in interstellar space, they do something stranger first. They form an atom. Not an atom in the ordinary sense. There is no nucleus. There is just an electron and a positron, orbiting their shared centre of mass, bound together by the same electrical attraction that binds an electron to a proton in hydrogen. Except that here the two partners have exactly equal mass, so neither one is orbiting the other. They orbit each other, like a binary star. The result is called positronium, and it is the lightest atom that can exist, and it is entirely made of things that are about to stop existing. Positronium was predicted in 1934 by a Croatian physicist named Stjepan Mohorovičić, and detected in a laboratory in 1951 by Martin Deutsch. It is a real substance in the sense that you can measure its energy levels. Its ground state binding energy is 6.8 electron volts, which is exactly half hydrogen's 13.6, for the simple reason that the reduced mass of the system is halved. The universe made a hydrogen atom out of antimatter and got the arithmetic exactly right, which is either reassuring or unsettling depending on your mood. And positronium comes in 2 versions, and the difference between them is the diagnostic that this entire field runs on. Every electron and every positron has spin, which for present purposes you can think of as an intrinsic rotation that can point one of 2 ways. When positronium forms, the 2 spins can either point in opposite directions or in the same direction, and which one you get is essentially a matter of chance. Because there are 3 ways to align spins and only 1 way to anti-align them, you get the aligned version 3 times as often. If the spins are opposite, the state is called parapositronium, and it lives for about 125 picoseconds. That is 125 trillionths of a second, the time it takes light to cross about 4 centimeters. Then it annihilates into exactly 2 photons, flying apart in opposite directions, each carrying 511 kilo-electron volts. 2 photons, 1 line, sharp. If the spins are aligned, the state is called orthopositronium, and here conservation laws step in and forbid the 2-photon exit. It is not that the 2-photon decay is unlikely, it is that it cannot happen. Orthopositronium is obliged to decay into 3 photons instead, and 3-body decays are slower and messier. It lives about 142 nanoseconds, more than 1,000 times longer than its counterpart, and when it goes, the energy is shared out among 3 photons in continuously variable proportions. So instead of a sharp line, you get a smeared continuum spreading downward from 511 kilo electron volts, with a distinctive sharp edge right at the top. Now put those two facts together with the 3-to-1 ratio. Most annihilations that go through positronium end up producing continuum rather than line, which means that if you measure the height of the line and the height of the continuum in the same spectrum, you can work out what fraction of positrons formed positronium at all before annihilating. That fraction has a name, the positronium fraction, and in the Milky Way it comes out close to the theoretical maximum of 1. Nearly every positron in our galaxy forms positronium before it dies, and a positronium fraction close to 1 is only achievable in one circumstance. The positrons have to be slow. A fast positron does not get captured. It rips past electrons far too quickly for one to fall into a bound orbit around it, and if it annihilates at all, it annihilates directly, in flight, producing that broad continuum at higher energies rather than a bound state. Only a positron that has been thoroughly slowed, down to energies well below a kilo-electron volt, essentially thermalized with the surrounding gas, will patiently form positronium and produce the signal we actually see. There is a laboratory version of this story that arrived recently, and it is worth a moment because it shows how hard the substance is to handle, even when you are holding it deliberately. In 2024, a collaboration at CERN called Aegis managed to laser-cool positronium for the first time. Laser cooling is a technique that has been used on ordinary atoms for decades. You shine light of a carefully chosen frequency at a cloud of atoms so that they preferentially absorb photons coming toward them and re-emit in random directions, which on average slows them down. It works beautifully on things like rubidium. It had never been done on an atom made half of antimatter, partly because positronium is extremely light and therefore extremely fast, and mostly because you have about 142 nanoseconds to do the entire experiment before your sample destroys itself. They got it from 380 Kelvin down to 170. A Tokyo-led group achieved a comparable result independently the same year. Physics World named it one of the 10 most important results in physics that year, and the reason is not the temperature. The reason is what it opens. If you can cool positronium far enough, you can in principle condense it into a single shared quantum state, a Bose-Einstein condensate made of matter and antimatter together. And such a condensate has been proposed as the working medium for a coherent gamma-ray laser. There is no such device. There has never been such a device. It would let you look inside atomic nuclei the way an optical microscope looks at a cell. I mention it because of the contrast. Cooling a puff of positronium by 200 degrees for 142 nanoseconds in one of the best-equipped laboratories that human beings have ever built is a landmark achievement. The Milky Way does the same physics, without supervision, 10 to the 43 times every second. So here is the chain, and I want to lay it out cleanly because everything that follows is built on it. The line we detect is narrow, which means the annihilating positrons are cold. The positronium fraction is near 1, which independently means the annihilating positrons are cold, but positrons are not born cold. The 2025 measurement says they are born at around 2 megaelectron volts, which is roughly 4 times their own rest mass. Therefore, every single positron whose death we observe has spent a long time between its birth and its death, doing nothing but slowing down. And slowing down, for a charged particle in interstellar gas, means collisions. It means passing near hydrogen atoms and knocking electrons loose, over and over, each encounter shaving off a small fraction of the energy. In typical interstellar conditions, that process takes something on the order of 100,000 to 1,000,000 years. During that entire time, the positron is not annihilating, it is travelling, which means the place where a positron dies is not the place where it was born, and the distance between those two places is the least well understood quantity in this whole subject. Let me make that concrete. Imagine you are that positron. You come into existence somewhere in the Milky Way, carrying about 2 megaelectron volts, which is a strange amount of energy for something that weighs half a megaelectron volt. You do not annihilate. You cannot. There is nothing that can catch you, because you are moving at a substantial fraction of the speed of light, and every electron you pass is a blur, so you travel. You pass through hydrogen atoms and knock their electrons loose, and each knock costs you a tiny sliver of your energy, and you slow imperceptibly. This continues for 100,000 years. 200,000. You drift through gas so thin that on Earth it would count as an excellent vacuum. You cross a light year, then 10, then 100, then something approaching 1,000, still slowing, still failing to die. And then, finally, when you're colder than the gas you have been swimming through, an electron catches you. For 142 billionths of a second, the two of you orbit a point in empty space, in the smallest atom the universe permits, and then there is nothing at all except 3 photons leaving in 3 directions, carrying away everything you ever were. That instant is the only part of that entire history that we can see. Not the birth, not the 100,000 years of travel, not the 1,000 light years, just the flash at the end. And that is the fact I want to leave sitting in the middle of this video, because it becomes the whole point later. We have never seen antimatter in the galaxy, not once. Across 55 years, a dozen instruments, thousands of papers and hundreds of careers, every single measurement in this field is a measurement of annihilation, a record of the moment the thing being studied stopped being the thing being studied. There is no photograph of galactic antimatter existing. There is no map of where it is. There is only a map of where it ends, which we have been treating as the same thing, only the death makes light. Which means that when astronomers finally built the deepest map anyone had ever made of that light, and found it glowing in places nothing should be able to reach, the first question was not what is making it. The first question was how any of it got there at all. Part 7. 20 Years of One Colour. On the 17th of October 2002, a Proton rocket lifted off from Baikonur carrying a European Space Agency observatory called Integral, the International Gamma Ray Astrophysics Laboratory. It was designed for a 2-year primary mission. It operated for more than 21 years, and it was finally retired in 2025, having outlived its design life by an order of magnitude, and having spent most of that time staring at a part of the spectrum almost nobody else was looking at. The instrument that matters for our purposes is called SPI, the spectrometer. It is built around cooled germanium, the same material that settled the argument in 1978, refined by 40 years of development, and it sees the sky through something called a coded mask. A coded mask is a clever solution to a genuinely awkward problem, which is that you cannot focus gamma rays. There is no lens for them. There is no mirror that reflects them at normal incidence. A gamma ray photon will pass straight through almost any optical element you put in front of it. So instead of focusing, you cast shadows. You hang a plate above the detector with a pattern of holes in it, and different directions in the sky project different shadow patterns onto the detector array below. Then you work backwards from the pattern of counts to reconstruct where the light came from. It works, and it produces images, but it is an inherently indirect method, and it is worth understanding that because it is the crux of everything at the end of this video. A coded mask instrument does not photograph the sky. It solves a puzzle about the sky. If your model of the instrument is slightly wrong, or your model of the background is slightly wrong, the solution to that puzzle can contain features that are not there. The background is the real adversary. SPI's dominant background is not astronomical at all. It is the spacecraft itself. Cosmic rays hammer the satellite continuously, and they induce radioactivity in its own structure, including, inconveniently, processes that generate positrons inside the instrument, which then annihilate and produce 511 kilo-electron-volt photons a few centimeters from the detector. The signal astronomers are chasing across 26,000 light-years is being manufactured, far more brightly, inside the box that is looking for it. Separating the two is the entire art. There is one saving grace, and the papers lean on it explicitly. The geometry of the instrument does not change with time. The background pattern in any given energy bin only changes when a detector fails, which happened a handful of times over 2 decades and is precisely documented. So the background can be modelled as something that is essentially fixed between known dates and calibrated over years of accumulated data. Which brings us to 2025, and to Hiroki Yoneda, Thomas Siegert and Saurabh Mittal, who did something with that dataset that had not been done before. They took 20.5 years of SPI observations, the entire mission, essentially from launch to retirement, restricted to a single narrow slice of the spectrum from 508 to 514 kilo-electron-volts, and reconstructed an image of the whole sky in that one colour, 20.5 years, 6 kilo-electron-volts wide. It is the deepest look anyone has ever taken at the annihilation sky. The reconstruction technique is called Richardson-Lucy deconvolution, and the idea behind it is straightforward even though the mathematics is not. You start with a guess at what the sky looks like. You compute what your instrument would have recorded if that guess were true. You compare that prediction to what the instrument actually recorded, and you nudge your guess in the direction that reduces the mismatch. Then you do it again, and again, thousands of times, until the guess stops changing. The technique is used across astronomy and medical imaging, and it is powerful. It is also, and everyone in the field knows this, capable of generating structure out of noise if you let it run too far, or if your model of the instrument is imperfect. The team knew that, so they did the obvious tests. They bootstrapped. That is, they generated many reconstructed images, adding random noise to the data each time, and asked which features survived. They ran reconstructions on background-only datasets to see what the pipeline produces when it is fed nothing at all, and they tested the response by masking the parts of the instrument model most likely to be wrong, the parts at large angles beyond the 16-degree field of view, and rerunning everything. The image came out almost identical. There is one more property of this dataset that has to be understood before the results make sense, and it is the single most important caveat in the entire story. Integral did not survey the sky evenly. Space telescopes point where the science is, and for 20 years the science was overwhelmingly in one direction. The galactic center is the brightest, richest, most competitive target in high-energy astronomy, and Integral's observing program reflected that. Enormous quantities of time went into the inner galaxy. Other parts of the sky got observed when something interesting happened there, or when a survey program swept through, or not much at all. The result is an exposure map that is wildly uneven. Some patches of sky have been watched for years of cumulative time, others have a few days, and crucially, the boundaries between those regions can be sharp. The papers note that a strong exposure gradient can appear across only a few degrees of sky. When you run a deconvolution across a boundary like that, the algorithm is being asked to reconstruct a smooth sky from data whose sensitivity changes abruptly. And that is exactly the situation in which reconstruction algorithms invent things. Everyone involved says so, repeatedly and in print. So the honest framing of the 2025 map is this. It is the deepest picture ever taken of the Annihilation sky, made with a method that is known to produce artifacts from data whose sensitivity varies by orders of magnitude across the field, using an instrument whose own body manufactures the exact signal being hunted. Every one of those is a reason for caution, and every one of them was tested as carefully as the team knew how to test it. Then they masked the galaxy. This part is important. Before you can ask what is in the sky away from the Milky Way, you have to remove the Milky Way, and you have to remove the things near it that produce 511 kilo-electron-volt light for boring reasons. So out went the galactic bulge, out went the thin disk and the thick disk, and out went a list of nearby star-forming regions where aluminium-26 decay would produce a genuine but uninteresting foreground. Orion and Eridanus, Taurus, Perseus, Scorpius and Centaurus, Cygnus, Carina, Vela, each with a margin around it to catch the surrounding hydrogen. Large parts of the galactic anticenter were masked too, including the Crab Nebula, because bright point sources distort a deconvolution. What is left after all of that masking is the high-latitude sky, everything more than roughly 15 degrees above or below the plane of the Milky Way. That is the part of the sky you look at when you want to look out of the galaxy rather than along it. It is where cosmologists point their instruments precisely because there is so little local material in the way. In visible light, it is the emptiest, cleanest part of the heavens. In gamma rays at 511 kilo-electron-volts it should be, to an excellent approximation, blank. There is essentially no dense gas out there to annihilate in, no population of stars manufacturing radioactive isotopes, no supernova, nothing. Blank was the expectation. Blank is what a null result would look like, and a null result was the reasonable prediction. Let me stop and put the pieces on the table before I tell you what happened, because we have covered a lot of ground, and the turn only lands if you're holding all of it at once. Fact 1. There is a signal, a narrow gamma-ray line at 511 kilo-electron-volts, coming from the Milky Way, detected continuously since 1970, confirmed by every instrument capable of resolving it. It is real, it is steady, and it is enormous, roughly 5 times 10 to the 43 positrons annihilating every second. Fact 2. The shape is wrong. The light concentrates in the old quiet bulge rather than the young active disk where every plausible positron factory actually lives. 55 years of candidates have failed on that geometry, and the 2025 measurement of the birth energy, about 2 mega-electron volts, eliminated most of the survivors. Fact 3. The positrons are cold. The narrowness of the line and the positronium fraction both demand it, which means they travel between birth and death for a very long time over a distance nobody can pin down. Hold those 3. Now here is what happened when the galaxy was subtracted out of the deepest annihilation map ever made. The sky did not go dark. Part 8. 6 places that should be empty. There were at least 6 of them. 6 patches of excess emission at 511 kilo-electron volts. Not 1, which would be an anomaly. Not 2, which would be a coincidence. 6 separate places in the sky where the deepest annihilation map ever assembled shows more light than there should be. All of them at galactic latitudes above roughly 15 degrees, sitting out in the part of the sky that was supposed to be empty. And they were not small. These were not point sources. Each one is an extended region spanning between 15 and 25 degrees on its long axis, which on the sky means something between 30 and 50 times the width of the full moon. In February of 2026, Thomas Siegert of the University of Würzburg and Hiroki Yonoda of Kyoto University submitted a paper to Astronomy and Astrophysics asking what those 6 patches were. It was accepted in May and published on the 16th of July, and the title tells you how carefully they were treading. Possible extragalactic positron annihilation signal. Possible. The word is in the title. Let me walk you through the 6, because the specifics matter and because a list of 6 independent places is a different kind of evidence than one anomaly. The first and brightest sites at galactic longitude 70 degrees and latitude plus 40, high in the northern sky. Its measured flux is 9.1 times 10 to the minus 5 photons per square centimetre per second, with an uncertainty of 2.6. That is a small number of photons in absolute terms. You would wait a very long time indeed to catch one with a handheld detector. But it is the brightest thing off the plane in this map, and its elliptical region spans 17.5 degrees. The second sits at longitude minus 100 and latitude minus 55, low in the southern sky, in the direction of the Magellanic Clouds. Its flux is 4.9 times 10 to the minus 5, plus or minus 1.6. Its region is the largest of the 6, 25 degrees on the long axis and strongly elongated, tilted about 10 degrees from the meridian, because the structure it traces is itself a long thin ribbon. The remaining 4 are fainter and are named for the constellations they sit in. There is a region toward Andromeda, at 4.3 plus or minus 1.6, a region in Ursa Major, at 2.4 plus or minus 1.3, a region in Hydra, at 2.5 plus or minus 0.9, and a region toward Virgo, the faintest of all, at 0.8 plus or minus 0.5. Add all 6 together, and you get 24 times 10 to the minus 5 photons per square centimetre per second, with a statistical uncertainty of 3.8 and this is the number that keeps the paper honest, a systematic uncertainty of 14.3. It is worth being precise about how those flux numbers were extracted, because the method is unusually candid, and it will matter when we weigh the result. The team did not have an automated source-finding algorithm draw the boundaries. They looked at the map and drew ellipses around the bright bits by eye. The paper says so directly. The regions were defined by visually setting elliptical boundaries around the hotspots, and the authors immediately add that this method might be slightly biased. Every ellipse in the table is specified by a centre, a semi-major axis, an eccentricity and a rotation angle, and those parameters were chosen by 2 humans looking at a picture. That is not a scandal. In a field where the features are diffuse and the statistics are thin, drawing regions by hand is a defensible choice, and the alternative, an automated finder tuned by the same humans, has its own biases. But it means the numbers in the table are answers to a question that was asked after the data had already been seen, which is a specific kind of statistical hazard with a specific name. We will come back to it. The uncertainties, meanwhile, come from bootstrapping. The team generated a large number of alternative reconstructed images by adding random Poisson noise to the dataset and rerunning the whole pipeline, then looked at how much the flux in each region wandered from image to image. The percentile spread across those samples is what the error bars represent. It is a reasonable approach. The authors also note, with some care, that because their procedure adds noise to the real data, rather than generating independent datasets, the degree to which the samples are truly independent is not straightforward. Now, at this point, a reasonable person asks the obvious question. 6 faint patches in a difficult reconstruction from an unevenly exposed dataset. So what? Astronomy produces marginal excesses constantly, and most of them go away. The answer is what they line up with. Take the 4 fainter ones first. The Andromeda region does not point at empty sky. It points toward the M31 group, our nearest large galactic neighbour and the swarm of dwarf galaxies around it. The Ursa Major region points toward the M81 group, another nearby concentration of galaxies, a few million parsecs out. The Hydra region points toward the NGC 3109 group, and the Virgo region points toward the Virgo cluster, the enormous collection of over 1,000 galaxies that dominates our corner of the local universe and that our own group is slowly falling toward. 4 faint patches of antimatter annihilation light, and all 4 of them happen to fall toward the 4 nearest large concentrations of galaxies in the sky. The authors are careful here, and I want to be careful too because this is where a story like this can go wrong. Those 4 regions have relatively little integral exposure. The paper says, in plain words, that there is no strong evidence that they are not background fluctuations, and later says there is a high probability that even all 4 combined are due to background. The systematic uncertainty on the 4 of them together is 10.1, which is to say, exactly equal to the signal itself. That is not a detection in any conventional sense. It is a suggestive pattern in noisy data. But then there are the first 2, and the first 2 are different, because the things they line up with are not millions of parsecs away, and cannot be dismissed as a coincidence of directions. The brightest hotspot, at longitude 70 and latitude plus 40, sits almost exactly on top of a structure that astronomers have been studying since the 1960s, and that has a name so drab it obscures how strange it is. It is called High-Velocity Cloud Complex C. The second, at longitude -100 and latitude -55, sits on the densest parts of the Magellanic Stream. Both of those are enormous clouds of hydrogen. Both of them have been mapped in exquisite detail at radio wavelengths for decades, by surveys that have nothing whatsoever to do with gamma-ray astronomy. When the team overlaid the hydrogen column density contours from those radio surveys onto their gamma-ray map, the 2 brightest off-plane hotspots landed on the 2 brightest off-plane hydrogen structures. That is a different quality of coincidence. The 4 extragalactic regions are pointing at directions on the sky, and directions on the sky are cheap. These 2 are landing on specific, mapped, physically characterized objects with known distances and known masses. And the paper's own summary of that situation is the sentence I keep coming back to. The extragalactic regions, they write, cannot be shown not to be background. But the more nearby regions of the high-velocity clouds, they write, can hardly be explained by background fluctuations. There is a second thing worth noticing about the 6, which is how they are distributed. They are not clustered. They are scattered across both galactic hemispheres, 2 in the north, 1 far down in the south, the others spread between, and they were identified in a single reconstruction rather than assembled from separate analyses. If a reconstruction algorithm is producing artifacts because of exposure gradients, you would broadly expect those artifacts to trace the exposure pattern, which is dominated by the enormous investment of time in the inner galaxy. These do not sit along that pattern in any obvious way. They sit, 4 of them, toward galaxy groups, and 2 of them, the brightest 2, on gas. So the question stops being whether the map has noise in it. Of course it has noise in it. The question becomes what those 2 clouds are, why anything in them should be glowing at the exact energy that means antimatter is dying, and how any antimatter could possibly have got there in the first place. And to answer that, you need to know what those clouds actually are, because neither of them is the kind of object you would ever nominate as an antimatter factory. Neither has the machinery, neither has the population. One of them does not even have stars, because one of them is falling into us from outside the galaxy, and the other one is not really a cloud at all. It is a wound. Part 9. What those 2 clouds actually are. High-velocity clouds were discovered in 1963, and for about 40 years afterwards nobody could say how far away any of them were. The discovery itself was almost accidental. Radio astronomers mapping neutral hydrogen across the sky, using the 21-centimeter line, which is the standard tool for finding cold hydrogen anywhere in the universe, kept finding gas moving at velocities that made no sense. The Milky Way rotates, and gas within the galaxy moves in a broadly predictable way depending on which direction you look. These clouds did not. They were coming in at over 100 kilometers per second, in directions where nothing in the galaxy should be doing that. The problem was that a radio measurement tells you a velocity but not a distance. A cloud could be a nearby wisp moving quickly, or a distant structure moving quickly, and the data looked identical, which meant that for 4 decades astronomers had a catalogue of large hydrogen clouds with well-measured velocities, well-measured masses per unit distance squared, and completely unknown positions in space. The solution, when it came, was elegant. If you can find a star of known distance that happens to sit behind, or in front of, one of these clouds, you can look for absorption lines in the star's spectrum. If the cloud's absorption shows up in the star's light, the cloud is closer than the star. If it does not, the cloud is further away. Bracket a cloud between 2 stars at known distances and you have bracketed the cloud. This became feasible only when large spectroscopic surveys had catalogued enough halo stars with reliable distances to make the sandwich work. Complex C is the biggest and best studied of them. It covers something like 1,700 square degrees of the northern galactic sky. For scale, the entire sky is a bit over 40,000 square degrees, so this single cloud is covering around 4% of everything, roughly the area of 8,000 full moons. It is falling toward us at around 130 kilometers per second. Its distance has been bracketed to somewhere between 4 and 12 kiloparsecs, which is to say between 13,000 and 39,000 light-years, comparable to our own distance from the galactic centre, and it contains at least 1 million solar masses of neutral hydrogen, possibly as much as 5 million. But the number that tells you what it is the metallicity. Astronomers use the word metal for everything heavier than helium, which annoys chemists and is extremely convenient for everyone else, because everything heavier than helium had to be made inside a star. Hydrogen and helium came out of the Big Bang. Carbon, oxygen, nitrogen, iron, all of that was manufactured in stellar interiors and scattered by stellar deaths. So the fraction of heavy elements in a body of gas is a direct measurement of how much stellar processing it has been through. Complex C comes in somewhere between 10 and 50% of the Sun's metallicity, depending on which sightline you measure. That is low. It is too low to be gas that was thrown out of the Milky Way's disk and is now falling back, because disk gas has been enriched over billions of years and would carry the galaxy's own chemical signature. Complex C's chemistry says it is comparatively fresh material, arriving from outside and possibly mixed with some galactic fountain gas along the way. There is a chemical detail about Complex C that has kept people arguing for 20 years, and it is worth a moment because it shows how much can be read out of gas. Alongside the low overall metallicity, the cloud shows a nitrogen deficiency, less nitrogen relative to other elements than you would expect if the material had been through a normal long history of star formation. Nitrogen is largely produced by intermediate mass stars over long timescales, so a shortfall of it suggests the gas has been enriched by a small number of massive star events and then left alone, rather than cycled repeatedly through generations of stars. Some interpretations have it as primordial gas that has picked up a light dusting of enrichment on the way in. Others have it as the stripped remains of a small satellite galaxy that came apart. A few propose that it is a mixture, genuinely external gas that has partially mixed with material blown out of the Milky Way's own disk and is now falling back. None of those interpretations gives it a way to make antimatter. All of them describe a body of gas with no significant star formation, no supernova rate worth the name, and no population of compact objects. Complex C is a large, cold, chemically simple body of hydrogen falling into a galaxy. That is all it is. So the brightest antimatter hotspot off the plane of our galaxy sits on top of 1 million-plus solar masses of relatively unprocessed hydrogen, falling into us at 130 kilometers a second from somewhere between 13 and 39,000 light-years away. The second hotspot is stranger. The Magellanic Stream was identified in the early 1970s, and it is not a cloud at all. It is a ribbon of hydrogen more than 100 degrees long, which means it stretches across more than a quarter of the entire circle of the sky. It trails behind the Large and Small Magellanic Clouds, our 2 most prominent satellite galaxies, and it is made of gas that has been pulled out of them. The mechanism is still argued about, some combination of tidal forces, as the 2 clouds swung close to each other and to the Milky Way, and ram pressure as they ploughed through the thin hot gas of our halo like a boat through water. Either way, the material was stripped out of the clouds over the past 1 to 2.5 billion years, and it is now strung out behind them in a stream that is, When you include the ionized component, one of the most massive gaseous structures in the entire local group. Its metallicity is around 30% solar, consistent with material that came out of the Magellanic Clouds rather than out of us. Distance estimates put it between 20 and 100 kiloparsecs, 65,000 to 326,000 light-years. The stream's shape is worth picturing, because it explains the elongated ellipse in the table. It is not a blob, it is a trail. The leading portion, ahead of the clouds, is often called the leading arm, and the long trailing filament behind them is the stream proper. The whole structure sweeps across the southern sky in a great arc, and it has been mapped in such detail by radio surveys that individual filaments and clumps within it have their own designations. Astronomers have been using it for decades as a diagnostic of the Milky Way's halo. The way it is being eroded and shaped tells you about the density and temperature of the hot gas it is moving through, which is otherwise almost impossible to measure. So when the gamma-ray map was overlaid on the hydrogen map, the brightest southern hotspot did not merely fall somewhere near the stream, it fell on the parts of the stream with the highest hydrogen column density. If you were designing a test of whether the annihilation is happening in that gas, that is what a positive result would look like. And here is the detail that makes the Magellanic Stream the cleanest target in this entire story. It has no stars in it. Not few, not faint ones. Searches have been done and no stellar population has ever been found in the stream. It is pure gas, hydrogen, and a trace of heavier elements, pulled out of two galaxies and left hanging in the halo. There is no star formation happening in it. There are no massive stars. There have been no supernovae. There are no neutron stars, no pulsars, no X-ray binaries, no accreting anything, which means that if there is antimatter annihilating in the Magellanic Stream cannot have made it. Let me put you in it for a moment because I think it is worth feeling. Imagine you are somewhere in the middle of the stream, 60,000 parsecs out, well beyond the edge of anything most people would call the galaxy. You would not know you were in it. The gas here is thinner than the best vacuum ever produced in a laboratory on Earth. Thin enough that you could sweep a cubic meter of it and gather almost nothing. There is no cloud to see, there is no glow, there is nothing overhead but stars, and the stars are all somewhere else. The Milky Way hanging on one side as a great wheel of light seen from outside, the Magellanic Clouds on the other, and between them, invisible, the 100-degree arc of hydrogen you're standing in, torn out of two galaxies more than 1 billion years before anything on Earth had a backbone. And in that emptiness, continuously, in the dark, individual electrons and individual positrons are finding each other, something on the order of 1,000 trillion times every second across the whole structure. A positron that has come from somewhere else meets an electron, and for 142 billionths of a second the two of them orbit, and then they are gone, and 3 photons leave in 3 directions carrying everything they ever were. Nobody has ever explained where those positrons came from. Nobody has proposed a mechanism that puts them there. The clouds have no engine, and the only place within reach that has an engine capable of producing antimatter at this rate is the Milky Way itself, which is why the entire argument now comes down to a single question about distance and speed. Because the gas has no stars, and the distances involved are, when you actually write them down, absurd. Part 10. The Journey That Cannot Happen. Everything in this video now collides in a single sentence, so let me say it as plainly as I can. To make the light we are seeing, a positron has to be slow. To get to where we are seeing it, a positron has to be fast. It cannot be both. Let me build that properly, because it is the heart of the thing. We know the positrons annihilating in those clouds are cold. We know it for the same 2 reasons we know it everywhere else. The line is narrow, and positronium forms. A positron moving at any appreciable fraction of the speed of light does not produce a narrow line at 511 kilo-electron volts. It produces a smeared Doppler-broadened mess, or it annihilates in flight and produces a continuum at higher energies. The only way to get the specific signal that was detected is for the positrons to have thermalized, to have slowed down to energies below about a kilo-electron volt, essentially matching the temperature of the gas around them. Now look at the distances. Complex C is between 4 and 12 kiloparsecs away. Call it 13,000 to 39,000 light-years. The Magellanic Stream is between 20 and 100 kiloparsecs. Call it 65,000 to 326,000 light-years. 326,000 light-years. Sit with that for a second. The visible stellar disk of the Milky Way, the whole thing from one edge, through the center, out to the other edge, is about 100,000 light-years across. The far end of the Magellanic Stream is more than 3 times that distance from us. If the positrons annihilating out there were produced in our galaxy's disk, they have travelled more than 3 galaxy widths from the place they were born to the place they died. And a cold positron does not do that. A cold positron does not travel any meaningful distance at all, because a cold positron annihilates. That is what cold means, in this context: slow enough to be captured, slow enough to form positronium, slow enough to stop. Follow one and you can feel the problem. It is born in the disk at around 2 mega-electron volts. It is fast, moving at a substantial fraction of the speed of light, and it starts to travel outward, but the disk is full of gas. Every hydrogen atom it passes near costs it a little energy. It rises out of the plane, and above a few thousand light-years the gas thins dramatically, so the energy loss slows down and it can keep going. It crosses the halo. 10,000 light-years, 20, 50. The Milky Way is now a wheel of light receding behind it. It crosses 100,000 light-years, more than the entire width of the galaxy it came from. It keeps going. 200,000. And at 300,000 light-years it finally arrives in a ribbon of hydrogen that was torn out of 2 other galaxies 1 billion years ago, and there, at last, it slows enough to be caught and dies. That journey takes, at a minimum, hundreds of thousands of years. In practice, given that this is diffusion through a tangled magnetic field rather than a straight line, it takes far longer. The path is not a line, it is a random walk, and a random walk covers ground with the square root of time rather than in proportion to it. A charged particle in a magnetized medium does not travel. It wanders tethered to field lines scattering off irregularities, and the whole time it is wandering, it is losing energy. That is the trap. The very process that eventually makes it visible, the slowing, is happening continuously throughout the trip, and the trip is enormously long. The standard expectation from positron transport modelling, which is admittedly uncertain, is that a positron born at a couple of mega-electron volts will slow to thermal energies after travelling something on the order of a kiloparsec. A few thousand light-years, enough to blur the map of where the sources are, nowhere near enough to leave the galaxy. So one of the things we're confident about is wrong. There are only a few ways out of that, and the paper works through them honestly. The first way out is that the positrons are made out there. Something in complex C, and something in the Magellanic Stream, is producing positrons locally, in place, so no journey is required. The trouble is that neither cloud has anything that could do it. The stream has no stars at all, not a population, none. Complex C has no significant star formation, neither has supernovae, neither has compact objects, neither has any of the machinery that appears on the suspect list. You cannot solve the transport problem by moving the factory if there is no factory to move. There is a third possibility that has to be named even though it is the least satisfying, which is that the coincidence is not physical at all. Both Complex C and the Magellanic Stream are large structures at high galactic latitude, and large structures at high galactic latitude are exactly where an imaging algorithm working on unevenly exposed data might be expected to place spurious extended features. If you draw a big ellipse anywhere in the northern high-latitude sky, you have a reasonable chance of overlapping Complex C, simply because Complex C covers 4% of everything. That objection is real, and we will give it its full weight shortly. But notice that the objection cuts less cleanly than it first appears. The hotspots do not merely overlap the clouds. The brightest parts of the gamma-ray regions fall on the highest column density parts of the hydrogen, and the same map produced 4 other regions that fall toward galaxy groups, which is a different sky and a different kind of target. An artifact that lands on the 2 biggest gas structures and the 4 biggest galaxy concentrations is doing a great deal of work. The second way out is that the positrons escape the galaxy fast and slow down on arrival. This is the interesting one, and it is essentially what the paper proposes. If positrons are swept out of the disk by a galactic outflow, a wind of hot gas rising out of the plane, of the sort that many galaxies, including probably our own, do generate, then they are not diffusing on their own. They are being carried. Material moving outward at hundreds of kilometers per second can take particles with it, and the halo through which it travels is very nearly empty, so the energy losses along the way are small. Then, when the outflow slams into something dense, a high-velocity cloud falling in, a ribbon of stripped hydrogen, the positrons finally encounter enough material to stop in. They thermalize on arrival, They form positronium. They annihilate coldly, exactly as observed, tens or hundreds of thousands of light-years from home. It is a coherent picture. It is also a demanding one, and the paper does the arithmetic on how demanding. The relevant quantity is the escape fraction. What proportion of the positrons produced in the galaxy get out of it before annihilating? For sub-giga-electron-volt cosmic rays, models of galaxies as leaky boxes give escape fractions in the range of 10 to 40%. That is the benchmark. If only complex C is being fed by the Milky Way, if the Magellanic stream signal comes from the Magellanic Clouds themselves, which are after all galaxies with their own stars and their own supernovae, then the implied escape fraction for the Milky Way is around 40 to 50%. High, at the very top of the expected range, but not insane. If both clouds are being fed by the Milky Way, the implied escape fraction is above 90%. That is very hard to defend. It would mean that the overwhelming majority of the antimatter our galaxy produces never annihilates inside the galaxy at all, that the signal we have been studying for 55 years, the one that has consumed careers, is the small remainder that failed to get away. The authors lean toward the more conservative reading, and they cite a curious piece of supporting evidence for the general idea. William Weber, working from the cosmic ray electron spectrum measured by Voyager after it crossed out of the Sun's influence and into genuine interstellar space, estimated that electrons below about 30 megaelectron-volts might escape the galaxy with fractions above 90%. Electrons, not positrons, and positrons should do worse because they have the option of annihilating on the way. But it establishes that very high escape fractions for low-energy particles are not a fantasy. A spacecraft launched in 1977, now more than 24 billion kilometers from home, is contributing a data point to an argument about antimatter leaving the galaxy. There is one more consequence of the escape picture that deserves to be said out loud, because it inverts the way the problem has been framed for half a century. For 55 years, the positron puzzle has been treated as an accounting problem within a closed system. The galaxy makes X positrons, the galaxy annihilates X positrons, and the challenge is to identify the sources that supply X. Every candidate on the suspect list was judged by whether it could deliver the required number inside the galaxy. If a large fraction of the positrons leave, then the number the sources have to supply goes up, and the geography of where they annihilate stops being a straightforward map of where they were made. The bulge versus disk problem, the thing that has broken every candidate for 5 decades, was always a comparison between two regions inside a box. If the box has been leaking the whole time, and leaking preferentially from the part with the outflows, then the comparison was never measuring what people thought it was measuring. That does not solve the puzzle. Nobody should claim it does. But it changes the shape of the question in a way that has not been available before, and it does so on the strength of 6 faint patches of light in a place that was supposed to be empty. Either way, the conclusion is the same, and it is the thing this whole video has been walking toward. If any of this is right, the Milky Way is not a closed container. Part 11. Counting. What we could not see. So how much antimatter are we actually talking about? Start with what those two clouds are consuming. Taking the measured fluxes and folding in the distance ranges, the annihilation rate inside complex C works out to somewhere between 0.1 and 4.5 times 10 to the 42 positrons per second. For the Magellanic stream, the range is far wider, because the distance is far less certain, anywhere from 0.8 to 156 times 10 to the 42 per second. If you assume both are annihilating under ordinary interstellar conditions, the numbers settle at about 1 and about 34 times 10 to the 42 per second respectively. Those are already large. 10 to the 42 positrons per second, in gas that has no stars in it, is a considerable amount of antimatter to be destroying. Now do the correction that turns this from an oddity into a headline. Those 6 regions cover only about 6% of the high-latitude sky. If the galaxy is leaking positrons roughly isotropically, if the outflow goes in all directions rather than only toward the 2 clouds we happen to be able to see, then what we are measuring is 6% of the total, and the rest is annihilating in gas too thin or too far away or too poorly placed for us to detect. Scale it up, and the implied outflow reaches somewhere between 5 and 7 times 10 to the 44 positrons per second. The paper's own phrasing for that figure is careful and blunt at the same time. It would be, they write, potentially stronger by more than 10 times than the galactic value. More than 10 times. meaning that if the isotropic leakage picture is right, everything measured inside the Milky Way over 55 years, the entire 5 times 10 to the 43 per second that has driven this whole field, is less than a tenth of what our galaxy is actually producing. The paper does not commit to that upper branch, and neither should we. They adopt a more conservative figure for the rest of their analysis, a total galactic positron production rate of about 10 to the 44 per second, which is a factor of 2 to 3 above the interstellar medium-only value. That number folds in the halo and high-velocity cloud contributions without assuming the most aggressive version of the leakage. A factor of 2 to 3 does not sound dramatic after 10. But think about what it means. It means that a quantity astronomers have been measuring, refining, arguing about, and building whole careers around for half a century was wrong by a factor of 2 or 3, and it was wrong in a specific and slightly humbling way. It was not a calibration error. It was not a modelling mistake. It was a horizon problem. We were counting the annihilations that happened close enough for us to see, and we'd quietly assumed that was all of them. There is one more branch, and it is the one the paper actually prefers. If the Magellanic Stream signal is being fed not by the Milky Way, but by the large and small Magellanic Clouds themselves, which are, after all, real galaxies, with stars, star formation and supernovae, then the Milky Way's own outflow drops to 3 or 4 times 10 to the 43 per second. That version is more comfortable, because it keeps the escape fraction near the top of the plausible range instead of above 90%. It is also, in a way, more interesting, because it means the clouds are doing it too, which brings us to the 4 fainter hotspots, and to the most quietly ambitious calculation in the paper. The team took a catalogue of nearby galaxies, roughly 1,600 of them, out to about 30 megaparsecs, essentially every galaxy in the local volume that anyone has catalogued, and asked a simple question. If each of those galaxies produces positrons in proportion to some power of its blue band luminosity, and if you add up the expected flux from all of them in each of the 4 directions, what power do you need to match the observations? The answer is a number that ought to make people uncomfortable. The exponent comes out at 0.25 plus or minus 0.03. An exponent of 1 would mean positron production scales in proportion to luminosity. A galaxy 10 times brighter makes 10 times as many positrons. That is roughly what you would expect if the positrons come from stars and stellar deaths, because luminosity tracks stellar mass and star formation. An exponent of 0.25 means something very different. It means a galaxy 100 times more luminous than another produces only about 3 times as many positrons. That is a remarkably flat relation, and nobody has an explanation for it. It says that positron production is only weakly connected to how many stars a galaxy has, which is either a sign that the whole model is too crude to trust, a real possibility, and the authors flag that the predicted fluxes come out somewhat below the observed ones, suggesting missing sources or hidden variables, or a sign that the process making these positrons is not primarily a stellar process at all. And then the model makes a prediction that I have not been able to stop thinking about. Run the scaling law over the catalogue and ask which individual galaxies should be bright enough for a future instrument to resolve. 10 or so come out above a threshold of 10 to the minus 6 photons per square centimetre per second, and the list includes exactly the objects you would expect: Andromeda, the Triangulum Galaxy, IC10, NGC 185. Big, nearby, well-known systems. But 4 sources come out an order of magnitude brighter than that, and all 4 of them are dwarf galaxies. The 2 brightest are Triangulum 2 and Ursa Major 2, at around 2 times 10 to the minus 5 photons per square centimetre per second, comparable to the entire Magellanic Stream region. Triangulum 2 and Ursa Major 2 are ultra-faint dwarf spheroidals. Their total luminosity is on the order of 1,000 suns, which is less than a single decent star cluster. They contain almost no gas. They have essentially no ongoing star formation. If you were listing objects in the sky by their capacity to manufacture antimatter, they would be at the very bottom. They are also among the most dark matter-dominated objects known to exist, with mass-to-light ratios in the hundreds, and in some estimates the thousands. That is why they are among the most heavily observed targets for dark matter searches in the entire sky. Now, the paper does not say what I'm about to say, and it is important to be clear about that. The paper mentions dark matter exactly once, as a possible hidden variable, and explicitly warns against overinterpreting the current findings. That is the correct and professional position, and I am not going to pretend otherwise. but the implication is sitting there in the table, and the honest thing is to name it as a question rather than an answer. If the brightest individual extragalactic sources of antimatter annihilation light turn out to be objects that have almost no stars and almost no gas, and a great deal of dark matter, then the idea that was constrained into a corner 20 years ago walks straight back into the room. Not proven, not even supported yet, but testable, which is a great deal more than it has been for 2 decades. The paper goes one step further than the local volume, and the last calculation in it is the one with the widest reach. If every galaxy makes positrons in some proportion to its star formation, and if star formation across the history of the universe follows the standard measured history, which peaks around 10 billion years ago at roughly 10 times the present rate and has been declining ever since, then there ought to be a faint uniform haze of annihilation light filling the whole sky. Not from any particular direction. From everywhere, accumulated over cosmic time, redshifted by the expansion of space so that light emitted at 511 kilo-electron-volts arrives at lower and lower energies depending on how far away and how long ago it was made. The estimate is that this contribution to the cosmic gamma-ray background is small, subdominant, at around the percent level, but it could rise above 10% at energies above a few mega-electron-volts if the positrons are being injected at high energies, because in-flight annihilation shifts the emitted spectrum upward, and the signature would be distinctive, a sharp cut-off right at 511 kilo-electron-volts, or a spectrum that rises as you go below it. There is a horizon built into this, and it is closer than you might think. The expansion of the universe shifts the line downward in energy, and the analysis window is only 6 kilo-electron-volts wide. Sources out to about 15 megaparsecs still land inside it. The Fornax cluster, at about 19 megaparsecs, is already half out. Its line would arrive centered at 508.7 kilo-electron-volts. The Coma cluster, at about 100 megaparsecs, is entirely gone. Its annihilation line arrives at 499.5 kilo-electron-volts, well outside the band. So this technique can only see the local universe as a set of individual places. Everything beyond blends into a haze. And step back from the specific objects for a moment, because there is something larger in this section that is easy to miss. If the scaling law is real at all, then this is not a Milky Way story. Andromeda, the smudge you can see with your naked eye from a dark field, the width of several full moons, 2.5 million light-years away, is leaking antimatter into the space around it right now. So is Triangulum, so is every galaxy in the M81 group, and the Virgo cluster, and every galaxy and every photograph ever taken. They have all been doing it for 10 billion years, quietly, invisibly, and the only reason we have ever noticed is that 2 of the clouds it happens to be running into are close enough to us to resolve, which is where the honest part of this video has to begin, because everything I have just told you is sitting on evidence that is much weaker than the story deserves. Part 12. All the reasons not to believe this yet. Now let me take the whole thing apart, because a video that presents this as settled would be lying to you, and the honest version is more interesting anyway. The significance is weak. That is the first and largest problem. The only figure available anywhere in this work is inherited from the 2025 imaging paper, and it says that individual regions were estimated at between 2 and 4 sigma each. Not 4. Between 2 and 4. Sigma is a measure of how unlikely a result is to have arisen by chance. 3 sigma corresponds to roughly a 1 in 740 chance of a fluke. 4 sigma is about 1 in 16,000. 5 sigma, the conventional threshold for calling something a discovery in physics, is about 1 in 3.5 million. The Higgs boson had to clear 5 sigma in 2012 before anyone was allowed to say it existed, and that was after decades of theoretical expectation. These hotspots are sitting at 2 to 4, with no theoretical expectation behind them at all, and even that understates it, because of how the regions were chosen. The team looked at the map, saw bright patches, and drew ellipses around them. That is a look elsewhere problem, and it has a formal name, the trials factor. If you scan a large sky for excesses and then compute the significance of the biggest one you found, you have to correct for the fact that you had many chances to find something. The more places you looked, the less impressive the best result is. No trials factor is applied anywhere in this paper. No look elsewhere correction is discussed, and the authors do not hide it. They state plainly that they focused on the scientific interpretation in the case of future confirmation and not on a detailed discussion of the detection significance. That is an unusually candid sentence to find in a published paper, and it should be taken at face value. This is not a detection claim. It is a what-if, worked through carefully, in advance of the data that could actually settle it. The systematic uncertainties are brutal. For the 4 extragalactic regions combined, the flux is 10.1, with a statistical uncertainty of 2.4 and a systematic uncertainty of 10.1. The systematic error is the same size as the signal, and the authors write in as many words that there is a high probability that even these 4 regions combined are due to background fluctuations. The exposure problem is real. Integral's coverage of the sky varies enormously, with sharp gradients over a few degrees, and reconstruction algorithms are known to produce structure at boundaries like that. The instrument response might be flawed. The paper says so directly. It might still be the case that the response itself is imperfect, that the background modelling still leaves systematics, or both. And there is the history. This exact corner of astronomy has produced confident structural claims before. The variability of the 1980s, which was an artifact of aperture. The Annihilation fountain of 1997, which was not there. The lopsided disk of 2008, published in Nature and proposed as the solution to the whole puzzle, which faded as data accumulated. 3 times a structure appeared in this map was reported responsibly and dissolved. So there are 4 separate, serious, individually sufficient reasons to be skeptical, and the authors of the paper raise all 4 of them themselves. There is one more twist in the statistics, and it runs in the opposite direction to everything else I have just said, which is why I want to give it its own moment. The uncertainties quoted throughout this work come from bootstrapping, resampling the data with added noise and seeing how much the answer moves. That is a conservative method by design. When the team compared their bootstrap intervals against a more conventional likelihood-based model fit for the total galactic flux, they found a discrepancy of a factor of 2 to 3, with the bootstrap intervals being the wider ones. And there is a known effect in this literature where neglecting covariance between parameters can inflate uncertainties by a factor of 2 or more, which means the error bars in this paper may well be too big. The authors chose to keep them anyway, because they were not trying to claim a detection, and a conservative interval was the appropriate choice for the argument they were making. But it is worth knowing that if somebody does the full statistical treatment properly, the significance is more likely to go up than down. That is an unusual direction for a caveat to point, and it is the reason this result has not simply been dismissed. Now here is the other side, and I think it is stronger than it looks. The response test is the most important piece. The team masked the parts of the instrument model most likely to be wrong, the regions at large angles, beyond the 16-degree field of view, where the response is least well characterized, and reran the entire reconstruction. The image came out almost identical. That does not prove the response is right. It does mean the features are not being generated by the part of the model most likely to generate them. The second piece is independent confirmation, and it comes from an unexpected direction. In 2016, a balloon-borne instrument called COSI flew from Wanaka in New Zealand on a long-duration flight. It was a completely different instrument from SPI, different detectors, different geometry, different background, different everything except the material and the target. And when its data were analysed and published in 2017 and again in 2020, it appears to have seen some of these same high-latitude features. 2 instruments, a decade apart, with nothing in common but germanium and a direction to point, showing structure in the same places. That is not proof. It is the single strongest circumstantial argument in the entire story, because an artifact of integral's coded mask has no business appearing in a balloon payload's data. And then there is the paper's last sentence, which is the sharpest thing in it and which I think earns the whole 8 pages. While there is still a chance that some of the high-latitude features are imaging artifacts, they write, it appears at odds if all hotspots are mere background fluctuations. That is the honest position. Any one of the 6 could be noise, any 2 could be noise, all 6 being noise, with the 2 brightest landing on the 2 most conspicuous gas structures in the off-plane sky, and 4 more falling toward the 4 nearest galaxy concentrations, is a harder thing to believe than the alternative. While we're being honest about what antimatter is and is not, there is a story from earlier this year that puts every number in this video into perspective, and I want to tell it properly. On the 24th of March, 2026, a collaboration at CERN called BASE did something that had never been done. They loaded 92 antiprotons into a portable trap, a device called Base Step, weighing 850 kilograms, containing a superconducting magnet, a reservoir of liquid helium, batteries, and a vacuum chamber holding the particles in a cage made purely of electric and magnetic fields, because any contact with an ordinary wall would destroy them instantly. Then they craned that box onto a truck. The loading took hours. The truck drove at something close to walking pace, a few kilometers, around CERN's own site at Meyrin. Then it came back, the box was plugged in, and the count was taken. 92. All of them. Still there. That is the first time in the history of our species that antimatter has been deliberately moved from one place to another and arrived intact. It is a genuine landmark, and the next step is a 10-hour drive to a quieter laboratory in Dusseldorf, where the magnetic environment is calm enough to push the precision measurements further than CERN's own antimatter factory allows. 92 particles. For contrast, consider what production actually looks like. Antimatter cannot be mined. It has to be manufactured, particle by particle, in accelerators, at an energy cost enormously greater than anything you could ever get back out of it. The total quantity of antihydrogen that CERN has produced across its entire history amounts to a few nanograms at the very most, and most estimates put it far lower. At current rates, producing a single gram would take something on the order of 100 billion years, roughly 7 times the current age of the universe. This is why the idea of antimatter as a suppressed energy source falls apart on contact with arithmetic. It is the most energy-dense substance physics permits, and that part is entirely true. Annihilation converts 100% of mass into energy, which nothing else does. But it is not a fuel, because there is no reservoir of it anywhere. There is nothing to withhold. Every antiproton in existence on this planet was made on purpose, at enormous expense, and there are not very many of them. Hold that number, because I am going to set it against something in a moment. Part 13. What is actually leaking? So let me answer the question this video started with, and I want to do it in 3 parts, because there are 3 different answers, and they get progressively less comfortable. The first answer is the literal one. What is leaking is positrons, antimatter, in the form of the electron's mirror twin, and it is leaking out of the Milky Way, not in a trickle. If the more conservative reading is right, our galaxy is producing around 10 to the 44 positrons every second, which is a factor of 2 to 3 more than anyone had measured, and a substantial fraction of them are escaping the disk entirely, riding outflows into the halo and annihilating when they finally strike something dense enough to stop them. The 2 places we can see that happening are a cloud of primordial hydrogen falling into us from 13 to 39,000 light-years out, and a ribbon of gas torn from our 2 nearest neighbours, as far as 326,000 light-years away. If the most aggressive reading is right, and the leakage is isotropic, the true production rate could be more than 10 times what has ever been measured inside the galaxy, 10 to the 44 per second. Now set that against the other number, the one I asked you to hold. 92. 92 antiprotons, moved a few kilometres across a car park in Switzerland at walking pace, inside 850 kilograms of superconducting magnet and liquid helium, and it was a world first, and it genuinely was. That is the entire scale of our ability to handle this substance deliberately. And every second, without any apparatus, without any supervision, without anyone having asked it to, the galaxy destroys something on the order of 100 trillion times that many, and has done so for as long as there have been stars in it, and will keep doing it long after everyone listening to this is gone. That is the first answer, and it is the smallest one. The second answer is what the disturbing part actually is, and it is not the antimatter. For 55 years, this field has been building a map. Every instrument, every balloon flight, every satellite, every reconstruction has been adding detail to a picture of where the Milky Way's antimatter is. The bulge is bright. The disk is faint. The ratio is 0.58. We have argued about that map for half a century and broken every candidate explanation against its geometry. But we were never mapping where the antimatter is. We were mapping where it dies. And more precisely, we were mapping where it dies close enough and densely enough for our instruments to register the flash. Those are not the same thing, and the difference is not academic. If a substantial fraction of the positrons leave the galaxy and annihilate hundreds of thousands of light-years away, in gas so thin that the resulting light is barely above the noise, then they were never in the census. They were not missing from the map. They were outside the region the map covered, and we had mistaken the edge of our sensitivity for the edge of the phenomenon. That is the disturbing part. Not that there is antimatter where it should not exist. It is that we spent 55 years explaining a distribution that may have been, in part, an artifact of how far we could see. The bulge versus disk problem, the thing that killed every candidate, was always a comparison between two regions inside a box we assumed was closed. Only the death makes light. That is how we find this substance. It is the only way we have ever found it, and it is the only way we will ever find it. But a technique that can only detect something at the moment it is destroyed will always, necessarily produce a map of destruction rather than a map of the thing, and a map of destruction has an edge, and the edge is set by your instrument, not by the universe. We were not looking at the galaxy's antimatter, we were looking at the portion of it that happened to die where we could see. And that brings me to the third answer, which is the one nobody can give. We still do not know what makes it. That has not changed. In fact, it got worse last year, not better. The 2025 measurement of in-flight annihilation gave us for the first time a direct read on the energy at which the galaxy's positrons are born, and the answer was about 2 megaelectron volts. And 2 megaelectron volts is too high for the radioactive isotopes we can inventory, and far too low for pulsars, cosmic rays, or anything relativistic. After 55 years of narrowing the field, we finally measured the one property that would identify the culprit, and it matched nothing on the list. So the honest state of this subject in 2026 is that we know a galaxy-sized quantity of antimatter is being created continuously, somewhere, by something. We know roughly how fast it is moving when it is born. We know how it dies in enormous detail, down to the width of the line and the fraction that forms positronium. We may now know that a great deal of it leaves before it dies, and we do not know what is making it. Not the mechanism, not the objects, not even the category. Something will change that, and it has a launch date. COSI, the Compton Spectrometer and Imager, is a NASA Small Explorer mission scheduled to fly in 2027. It will survey the entire sky from 0.2 to 5 megaelectron volts using cooled germanium detectors, with an instantaneous field of view covering more than a quarter of the heavens at once, which means it will not have the uneven exposure problem that has haunted every result in this video. Antimatter annihilation in the galaxy is one of its stated primary science goals, and it has already been to this particular scene of the crime. Its balloon-borne predecessor, flown from New Zealand a decade ago, seems to have seen some of these same high-latitude features. If the hotspots are artifacts, COSI will show a blank high-latitude sky, and this whole story will join the annihilation fountain and the lopsided disk in the file of things that were not there. If they are real, COSI should not only confirm them but begin to resolve individual sources, Andromeda, Triangulum, and possibly a handful of ultra-faint dwarf galaxies that have almost no stars, almost no gas, and an enormous amount of dark matter. If those turn out to be the brightest individual antimatter sources in the extragalactic sky, then a question everyone had quietly filed away 20 years ago is going to have to be opened again. It is worth saying clearly what would count as being wrong, because a claim that cannot fail is not worth much. If the hotspots are real, and the leakage picture is right, several things should follow, and each of them is checkable. The high-latitude features should persist in a completely independent instrument with even coverage, rather than fading as exposure improves. The brightest emission should continue to track the highest hydrogen column densities in Complex C and the Magellanic Stream, rather than drifting away from them as the maps sharpen. The Magellanic Clouds themselves should show annihilation emission, since under the preferred reading they are feeding the stream, and the line from these regions should stay narrow, because the whole argument depends on the positrons arriving and then thermalizing rather than annihilating in flight on the way in. Any one of those failing would do real damage to the story. All of them holding would make it very difficult to argue with. That is a good position for a claim to be in, and it is the reason this 8-page paper is worth 2 hours of anyone's evening, even though it does not prove anything. Either way, we will know within a few years of launch, which is a remarkable thing to be able to say about a problem that has been open since 1970. So this is where I will leave you tonight. Somewhere above the plane of our galaxy right now, in a cloud of hydrogen that is falling toward us out of the dark, and in a ribbon of gas that was torn out of 2 other galaxies before there was anything on this planet with a spine, individual positrons are meeting individual electrons. Each one of those positrons was born somewhere else, carried something on the order of 2 mega-electron volts, spent an unimaginable stretch of time slowing down, and crossed a distance greater than the width of the Milky Way before it found what it was looking for. And each of them, in the end, is the one that had no partner, the leftover from an accounting error at the beginning of time, finally, after all of that, finding one. We can only see the moment it happens. We have never been able to see anything else. And now we have found that moment happening in places nothing should have been able to reach, which means the honest summary of 55 years of work is not that we have found antimatter where it should not exist. It is that we finally found out how much of it we were never looking at.